I want to give you some insight into a more complex type of problem that the College Board loves to ask about, and that is a limiting reactant problem. Right? Limiting reactant problems. Let me just cover what a limiting reactant is. A limiting reactant is the thing that runs out. It's the reactant that is consumed first. In other words, it runs out, you don't have any more, so the reaction has to stop. For instance, if you are, say, burning a candle, typically the candle wax is the limiting reactant. Once you have burned up all of the candle wax, the reaction stops burning. We're actually going to work a problem with that in just a minute to kind of work through how things might play out if you, say, enclose the candle in a sealed up container with a limited amount of oxygen, which runs out first. So here is a stoichiometry problem. It's a complicated looking one. It says C31H64 plus 57 oxygens make 31 carbon dioxides and 32 oxygens. C31H64 is one of the ingredients in, say, candle wax. And then the problem says if 19.5 grams of C31H64 react with 250 milliliters of oxygen at 750 torr and 298 kelvins, how many molecules of carbon dioxide will be produced? So I'm starting you off with two different things. I'm starting you off with grams of C31H64, and then I'm starting you off with a volume, pressure, and temperature of oxygen. And I'm asking you about molecules of CO2. So let's handle the first part of this problem because that's the easiest thing to deal with. We have 19.5 grams of C31H64. Our first step is to convert those grams into moles, where 1 mole equals, now we need to figure out how many grams. And I'm coming up with 436.8 grams is a mole. And then our next step is to go from, and this is of C31H64. Then we need to go from moles of C31H64 to moles of CO2, because that's what it's asking us about in the problem. So you'll notice that our coefficients here, this is understood to be a 1 right there in front of the C31H64. And there's 31 in front of the carbon dioxide. Let me switch back to the pen mode. 1 and 31. And then our last step is to take our moles of CO2 and turn them into molecules. And that's where we use Avogadro's number, that 1 mole is 6.022 times 10 to the 23rd molecules. So then we work all this out in our calculator. And I'm coming up with 8.33 times 10 to the 23rd molecules of CO2. So that's the first half of working this problem out. The second half, we need to deal with the oxygen. And since we have been given a volume, a pressure, and a temperature, well, we can't do stoichiometry with those. We need moles. So we're using PV equals nRT, which can be rearranged to say that N equals PV over RT, where our pressure is 740 torr, Our volume in liters is 0.250 liters because there are 1,000 milliliters in a liter. The gas constant in torr, or in millimeters of mercury, the same thing, is 62.36 liters torr per mole Kelvin. And our temperature is 298 kelvins. Keep in mind, if I'd given you that in Celsius, you would have to convert it into kelvins. So we take 740 times 0.25 divided by 62.36. That's 298. And we come up with 0.00995 moles of oxygen. Then we can plug that in and do some stoichiometry. We have that many moles of oxygen. How many molecules of CO2 can we make with that? Well, we know that for every 57 moles of oxygen, we can make 31 moles of CO2. And then 1 mole of CO2 is 6.022 times 10 to the 23rd molecules. So we multiply all that out. And we get 3.26 times 10 to the 21st molecules of CO2. So now we need to evaluate our two answer choices and see which one of these two is the smallest. When we do that, this is our smallest number. So once we have produced this many molecules of carbon dioxide, we have used up all of the oxygen, and so the reaction has to stop. I will now demonstrate this reaction for you. I've got this candle wax, which I'm going to ignite. And then I've got this quarter-liter flask, 250 milliliter flask, which has oxygen in it. It's not pure oxygen, but we'll pretend for those purposes. I put the flask over the candle, and it's consuming the oxygen. There's water vapor being formed on the inside of the flask, and the candle has gone out. So you can see the water vapor that's one of the products of the reaction. But it's gone out because we have consumed all of the oxygen. So oxygen in that case was the limiting reactant. Had I not put the container over it, this candle would have burned up before it uses up all this oxygen in the room, which is fortunate because otherwise I would suffocate if that weren't the case. So now let's take a look at some problems that have been given on actual AP exams and how they relate to this. So here's a problem that says it gives us a reaction with Na2S2O3 plus 4 sodium hypochlorites plus 2 sodium hydroxides makes 2 sodium sulfates plus 4 sodium chlorides and water. Student performs an experiment to determine we don't know all those words yet, but it says, calculate the number of grams of Na2S2O3 needed to prepare 100 milliliters of 0.5 molar solution. So they've given us volume and molarity. We need to find moles and then convert that into grams because molarity equals moles over liters. We've got 0.5 molar and 100 milliliters is 0.1 liters. So we need 0.05 moles. And then in order to go from moles to grams, 1 mole equals the mass of sodium times 2 plus the mass of sulfur times 2 plus the mass of oxygen times 3, which is 158.12. And then we multiply that out, and we get 7.91 grams. Now, if you did not show your work in these steps, it would be wrong. Next, this says, in part C, it says, using the balanced equation for the oxidation reduction reaction and the information in the table above, determine which reactant is the limiting reactant. Justify your answer. Now, what you should notice is that our concentration and volumes are the same. So since we have the same constant molarity and the same volumes, we have the same number of moles of each of these things. So if we look at our reaction, it takes one of those and four of those and two of those to react. So it takes 4 moles of sodium hypochlorite for every 2 moles of sodium hydroxide and every 1 mole of sodium thiosulfate. The reactant that is limiting, the one that would be used up first, is NaOCl, because you have to say 2 things. We have the same number of moles of each reactant, and since NaOCl has the largest coefficient, it's used up first. So it has the largest coefficient. Why is this not coefficient? So it is used up first. There was another part of this problem that asked you to write a net ionic equation for this reaction up here. And that's a little bit trickier because when you break this up, you get 2 Na pluses plus an S2O3 with a -2 charge plus 4 Na pluses plus 4 OCl minuses plus 2 Na pluses plus 2 OH minuses, and that will yield 4 Na pluses plus 2 SO4 -2s plus 4 Na pluses plus 4 Cl minuses plus an H2O. That's a complete ionic equation. And then our spectator ions, we've got 2 plus 4 plus 2, that's 8 sodiums, so we can cross those out on each side. And then that's pretty much it for what we can cross out. So it's going to be an S2O3 -2 plus 4 OCl minuses plus 2 hydroxides makes 2 sulfates plus 4 chlorides plus a water. So that would be your net ionic equation. Now let's look at another problem. This one says carbon tetrachloride can be synthesized according to the reaction above. A chemist runs the reaction at a constant temperature of 120 degrees Celsius in a rigid 25-liter container. Chlorine gas is initially present in the container at a pressure of 4.4 atmospheres. How many moles of Cl2 are in the container? So take a minute and see if you can figure that out. And then, how many grams of carbon disulfide are needed to react completely with the chlorine? Keep in mind, this is the reaction, so try working that problem out. All All right. Another sample problem says a student is given 50 milliliters of a solution of sodium carbonate of unknown concentration. To determine the concentration of the solution, the student mixes it with excess calcium nitrate, causing a precipitate to form. The balanced equation is shown below. Write the net ionic equation for the reaction that occurs when the solutions of sodium carbonate and calcium nitrate are mixed. Well, when they're mixed, see, sodium carbonate is soluble, so it will break apart, as will calcium nitrate, and sodium nitrate's also soluble. So our sodium ions would cancel out in a net ionic equation, as would our nitrates. So the net ionic equation would be that calcium ions react with carbonate to produce calcium carbonate. And since it is a net ionic equation, you do need to put the charges on the calciums and the carbonates. Then it says the diagram below is incomplete. Draw the species needed to accurately represent the major ionic species remaining in the solution after the reactant is complete. So we have sodiums and nitrates. Those were our spectator ions that did not participate. But there is another thing, because this said we had excess 1 molar calcium nitrate. That means we added more than we needed, so there's some left over. So there should be some calcium ions in here, at least one of them. So calcium with a +2 charge should be present. Right? So that's all you needed to do, was draw in a calcium ion. Then this problem gets a little more complex. It says they filter and dry the precipitate and record the data in the table below. And it says determine the number of moles of sodium carbonate in the original 50 milliliter solution. So to find out how many moles of sodium carbonate we started with, this is a stoichiometry problem, where we have 0.93 grams of calcium carbonate, and we need to convert those grams into moles. We're going to take the mass of calcium plus the mass of carbon plus the mass of 3 oxygens, and that comes out to be 100.09 grams. And then if we look at the balanced chemical equation, for every calcium carbonate, we had a sodium carbonate. It's a 1-to-1 ratio. So 1 mole of calcium carbonate is 1 mole of sodium carbonate. So that means that we had our number of moles in the original solution. We should probably report this to 2 significant figures. Is going to be 0.0093 moles, which is interesting as a result. But that's what you get when you do this math. Then it says that the student realizes the precipitate was not completely dried and claims that as a result, the calculated molarity is too low. Do you agree with the student's claim? Well, if the precipitate was not dried all the way, then this mass would be larger, which would make then reality. That would make the moles bigger than we would expect. And since molarity equals moles over liters, that would give us an answer that's actually too high, not too low. You could actually plug in another number by saying If it were dried all the way, then the mass would be maybe 0.8 grams, and then do the math with that and get 0.008 moles divided by 50 milliliters and show how that would give you a result that is too small. How if it were dried, it would give you a smaller result, and since it's not dry, it gives you a larger result. And then the last thing it says, after the precipitate is formed and filtered, the liquid that passed through the filter is tested to see if it can conduct electricity. What would be observed? Justify your answer. Well, the liquid has all of these things in it. So there are ions of sodium nitrate, and calcium still in solution. And since ionic compounds conduct electricity, the filtrate would conduct electricity. So that would be how you work through that problem. So this was actually on the 2019 AP Chemistry exam, was that question. So I hope this helps a little bit with your understanding of stoichiometry and limiting reactants, and hope you'll have a great day.